All right. Welcome to my talk, and welcome to the, I believe, second edition of C++ Under the Sea. I'm super happy to be here. I was here a year ago, and yeah, super happy to be back, and thanks for coming to my talk. Let's hop into things. So this talk is entitled Functional GPU Programming, and it could have been titled Array GPU Programming. And we're going to come back to that, but I'm just highlighting it now. And we will answer, why are we calling this functional when it could have been called array? We're going to answer that question, I don't know, halfway through the talk. My name is Connor. I go by code_report online. I am on Twitter and YouTube, as you saw on the previous screen. I don't have the energy to go and add all of the Blue Sky and Mastodon links because they're rather long. If you go to plrank.com, it'll bring you to this website, which is one of the several websites that I manage. It shows programming language rankings, but then you can just click on one of these icons. So for whatever platform you're on, I know a lot of people are on a couple, some of you are only on one, used to be on others. If you want to follow me, just go click on one of those links. That's the easiest way to follow me online. This is the About Me slide. I technically haven't updated it in a year, but that's because nothing has changed. I still work at NVIDIA. I went from working at NVIDIA for 5 years to working at NVIDIA for 6 years. And all of the things, my favorite languages, the languages that I have the most experience with, are all the same. So if you've seen one of my talks before, you've seen this slide. Probably most interestingly, aside from the fact that I work at NVIDIA, is that I have 3 different technical podcasts. It was mentioned in the keynote just by Sean. ADSP, raise of hands if anybody has heard of it / listened to it. All right, so that's about half of the audience. If you are a listener for the first time ever, well, first time ever at this conference, second or third time ever, we have stickers. I actually don't know if I picked any up. I know Bryce has some. There are some down at the NVIDIA booth. I should probably have some on me later. I gave Bryce a hard time at only making 50 the last time we came to Europe a couple weeks ago. Now, I don't know how many we have, but we have hundreds, so we probably will not run out. So if you'd like a sticker, come and find us. And I also have 2 other podcasts having to do with array languages, which are going to come up a little bit in this talk. So everything I just mentioned, and including this, someone told me that I do a bad job of pointing out that I have a YouTube channel. So some people didn't realize that I was the person behind this YouTube channel. So there's a bunch of talks, programming language related. All of this content, the socials, the talks, the YouTube, the podcast can be found at this GitHub repository, code report /content. In the future, I should probably add a QR code as I've started using those. So I'm extremely excited today to announce that we are open sourcing, or I should say, have just open sourced a new algorithm library called Parrot. So I've been working on this for, if you include the former iterations, the last couple of years, but in the current incarnation that it's in for the last 7 or 6 months. And this is a high-level parallel array-based library with implicit fusion. And so we're going to talk about that in a sec. So we just open sourced this literally 30 minutes ago in Sean's keynote. And you can go and check this out at mblab/parrot. There is also here a QR code if you don't want to type this in. So literally, it was just open sourced under the Apache 2.0 license. I can even show you if we go hop over here. I guess this is supposed to be in full screen mode. That is not the shortcut for full screen. And you can see, we've just open sourced this. So I should note this is a research library. So NVIDIA manages 2 different GitHub organizations. Primarily, there's technically a few others if you include others. But there's NVIDIA and there's NV Labs. So NV Labs is for research libraries. Other libraries that live under the NVIDIA organization started off in NV Labs and then at some point transitioned over to NVIDIA. So you can scroll down here. If you want to come, create an issue, create a PR, fork it, mess around with it, you can. And it's also attached to working docs. These are the current docs. And, what you would expect for a modern library. You can search, etc. So let's get back to the slide deck. And now we have the overview of this talk. So first, we're going to start off by looking at a simple example to introduce this library. And we're going to compare it to C++23 Thrust, which is an existing NVIDIA library that provides you with a set of parallel algorithms. And then after we do that, we're going to look at an overview of the library API, follow that up with 2 other problems, and then if we have time, look at some profiling stuff. So the first problem is a very simple, trivial problem in hopes to not lose any of the audience or the future watchers on YouTube. And this is a sum of squares problem. So the idea is we're going to generate a sequence of numbers, square each number, and then add them up. Very straightforward. We've basically got a generation of a sequence, a mapping operation, and then a reduction operation. So first, we're going to do this in C++. And note that Ben Dean, fellow podcaster and one of my favorite speakers, he always likes to put a slide at the beginning of his talk. No AI was used in the generation of this talk. Mine says the exact opposite. AI was heavily used in the creation of this talk, including all of the code. So every single code example, basically, I start off by asking Claude 4. I use Cursor typically. I know Claude 4.5 just came out, but I still have been using Claude 4 because I think it works better with Cursor. And this is the code that it generated. So this is actually pretty decent. I asked specifically for C++23. I've seen a lot of stuff on LinkedIn and on the socials where they say like, oh, I asked for C++ and this is what it gave me, and it's giving some C++98. You need to be specific. If you specify the standard, it is more likely to use the modern features. This, however, does not compile. I'm going to give away the first reason because it's very hard to catch this. We do not have the correct headers. Fold left, even though it's inspired by the algorithms that live in numeric, actually lives in the algorithm header. So we're missing the algorithm header. That's not a terrible mistake by Claude. A ton of beginner developers would do this. On top of that, we don't actually need numeric. The iota algorithm that lives in numeric is not being used here. We're using views here. So those live in the ranges header, so we can actually get rid of the numeric header. And so now we have almost working code. At this point, I will ask the audience, does anybody know why this does not compile? And usually I have chocolates to throw out, but we're not going to do that today. But there's proverbial chocolates if you can figure out why this code doesn't compile. Something about lifetimes is not correct. It is not missing return. It's just slightly, or you mean return 0 from the main. That does not lead to a compilation error. It might, depending on the compiler they're using, but in order to compile this, you need C++23, I believe, for the fold left. And so that compiler should not choke on that. At least the one I was using was not. The answer is that fold left is not a view, and therefore it is not pipeable. So the views, iota and transform, both from C++20, you can pipe to each other. Algorithms, however, whether that's an iterator algorithm or a range algorithm from C++20, or one of the new, numeric, even though it lives in algorithm, they are not pipeable. There's no reason for this other than the committee decided that they only wanted to make the views pipeable because it's a lot of work to go back and make the algorithms pipeable. So in order to get this to compile, you need to move the fold left to the top and then pass the result of the iota pipe to the transform as an argument to fold left, which is unfortunate because it breaks the linearity of the readability of the code, but at least this works. So this is your C++23 modern solution to sum of squares. So, and I believe I'm showing here, this is, one of my pet peeves is Claude 4 used IOStream, but if you're using C++23, I recommend using the print. So I believe this brings us to the next solution, which is in Thrust. So if you're not familiar with Thrust, Thrust is probably one of the most well-known CUDA C++ libraries that provides parallel algorithms. It's inspired by the C++ standard algorithms. So a lot of the algorithms that you find in the C++ standard library, you can also find in Thrust, and they are parallelizable. So once again, I asked Claude 4, write me a version of this sum of squares, and this is what it gave me. So once again, the first issue with this code is it's messed up the headers. We're making use of a transform reduce to do both the transforming and the reducing in our solution. But you can see in the headers, it's included reduce, it's included transform, neither of which we need. We need the transform reduce. Therefore, we need to do this in order to get it to compile. And then we can also get rid of the reduce. I don't think we need functional, so there's a couple extra headers. Clearly, Claude 4 has trouble with headers. But after this, it is a fully working solution, even if suboptimal. So we have a function object, some people refer to these as functors, called square, that's just squaring our object, or our element one at a time. Then we make a call to the sequence algorithm, which is the equivalent of our iota algorithm in C++ 11. It was added, I believe. And then we make a call to transform reduce, where we pass our function object square. It's going to square each of our elements, and then we are going to do a plus reduction with the binary thrust plus operation. So a few things I would do to change this code. One, I would get rid of the comments because they're not very helpful. Two, this function object is a little bit outdated in my opinion. At one point, this was how you had to write code in order to accelerate it on an NVIDIA GPU. But at a certain point, we added a -- extended - lambda flag, which enables you to pass lambdas as long as they're annotated with the correct host and device annotations. So you can change this code to a thrust transform reduce that is just making use of a annotated lambda. So this is what I almost would prefer to see optimally. These are my first couple of major issues, and comments is not a big deal. However, there is one suboptimal thing that we're doing here that we could do much better. Does anybody know what it is? Reserve the vector. I mean, technically, we're doing that with the n. That is the equivalent of initializing and then calling a dot reserve. So the answer is that thrust sequence is an algorithm that we are using to get our iota sequence. But this is going to dispatch a kernel in order to do this computation. And on top of that, we're allocating this device vector in order to store that sequence. But in the previous C++ solution, because we were making use of a view, we were doing this lazily and we never had to allocate any memory. And so the preferred solution, in my opinion, is to use a lazy version of this sequence algorithm, which unfortunately is called something different. It's called a counting iterator. So now we have three names for the same algorithm. We've got views iota, technically the algorithm iota. Then we've got sequence, which is the algorithm version of that. And then we have counting iterator, which is our lazy version of it. So a little bit hard to keep all of this straight. But in this code now, we no longer are allocating memory for our basically sequence or iota operation. We've bundled this all together. And so at the end of the day now, this code only launches a single kernel, which is effectively your reduction. And all of the generation of your integers, the mapping of your square operation is all done in that same kernel, which is fantastic. This is the ideal code, in my opinion, that you want to write. A little bit unfortunate, though, that you have to kind of keep this stuff straight in your head. One of my API philosophies, especially in the age of LLMs, is becoming delineation is a bad thing. When you have both views and algorithms, when you have both what counting iterator, it's an iterator or a fancy iterator, and algorithms, you're giving the LLM two things to choose between. And a lot of folks struggle with this. They put code online, so it's just a token predictor. It's going to predict what they think the most likely thing is, which that's not technically the best thing. If you can provide an API that hides this complexity, you've already chosen it behind the scenes, just give the LLM one thing to generate, you're going to end up with better generated code. But still, this is pretty good. This is what we have today. And this is just an alternative kind of piece of code showing my point. These two pieces of code, a counting iterator passed to a transform reduce, or a counting iterator passed to a transform iterator, passed to a reduce, are semantically equivalent. But there's two different ways to spell them. And which one is preferred? I would argue that transform reduce is preferred because it is the specific, most specialized algorithm here. But you could make an argument that like these are the more fundamental, separate blocks, and chaining these together is a better thing. It's up for debate. And this brings us to Parrot. So this new library, high-level, array-based, parallel. The following is how you would solve this in Parrot. Sum of squares, you start with an integer. A fourth name for our algorithm. It breaks my heart not to call this iota because I love APL and that's where the name comes from. But I used LLMs in the creating of this library, and it was very adamant that I not choose the word iota for it. It said 90% of libraries and languages call this range. You should just use range. And so I listened to the LLM. So this generates your sequence. You call .sq for square, and then you call .sum, and you're done. So this is extremely elegant in my opinion compared to what we had before. And there's a lot of niceties here. You know, in the first couple versions of this presentation that I gave, I didn't highlight this. But one of the really nice things, and one of the complaints about you know, ranges and things like that, it's hard to debug. Because this is a single class where every algorithm and operation is a method, if you want to debug a sequence of these operations, you can just inject print at any point in time, and it'll basically print out the state of your computation at that point in time. So that's super nice. This is the full code, just to compare it to the thrust in C++, because we had the full code there. So all of the headers that you had to include are just, you know, hidden behind the scenes from the parrot.hpp. And on top of this, you know, I'm formatting it with like the waterfall formatting, but technically this is what Clang format would do with my file. A lot of the times I prefer to see it chained, even if it doesn't hit the line limit that, you know, curtails it down. But nice that you can kind of read it this way. So that is the first example. Hopefully you were able to follow that. So let's take a look at the Parrot API. We're not going to go through every single one of these operations, but at a, you know, 30,000 foot view, this is what the API consists of. At this point, we're gonna take a break to talk about the functional versus array. So I mentioned that the title of this talk is called Functional GPU Programming, but it could have been called Array GPU Programming. What do I mean by this? This has recently been a thought that I've been having, is that array programming is just functional programming plus rank polymorphism. And on top of this, the languages that I am very fond of, that I talk about on my other podcasts, Iversonian array languages are just functional programming plus rank polymorphism plus symbols. So not all array languages look like APL, if you're familiar with that. Some of them, you know, like R and Julia, they're just keyword languages. And they're still considered, in my opinion, both array and functional languages. This is another way to visualize this. You know, Iversonian is a subset of array, which is a subset of functional. And when I made this slide, I realized actually a few years ago, I made a different version of this, and then I added it to compare. And it's kind of interesting, because if you look at this, this is not consistent with the last slide that I showed. The functional languages are the blue circle, which are not a superset of everything. And the reason is because of the array languages that are not functional. You know, some of these actually are, like I think Julia and R, I would consider, they have a lot of functional features, especially Julia. However, NumPy lives inside of Python. Even though that may have functional features, I wouldn't consider it a functional language. And MATLAB and Fortran definitely are not functional. So, you know, with a grain of salt, think about that functional equals array plus rank polymorphism. So I've been saying rank polymorphism. A couple of you might know what that means, but it is a very fancy term for being able to do things without iteratively calling maps or loops. So everything on the left here, which I've done, I see I'm running into the same problem that Shantan ran into. Everything here is rank polymorphic. So when you see map, this is slightly different to the transform that you see in ranges or the map that you see in functional languages. So what do I mean by that? This is one way you might add 1 to a matrix or to a vector of vectors in C++. This honestly is probably the nicest way to do it. I did this in ranges. It sadly took me 20 minutes to get this compiled because I had left off the reference and was using references inside. And so when I was asking the LLM, it was just going nuts. And then I had to kind of ignore it for a while. And then finally I got it working. But even after I got it working, this is not that elegant in my opinion. And so what is it in Parrot? It's just the following. You just add 1. And so whether you have a vector, which is a rank 1 array, or a matrix, which is a rank 2 array, or all the way up to some arbitrarily ranked array, any kind of binary or unary operation you can just apply to every element in the matrix. Which means that this nestedness, whether you're using ranges or loops, you can avoid. And this is not a new thing. If you've ever done NumPy coding or MATLAB coding, this is like a built-in feature. NumPy calls it something different. They call it broadcasting. And honestly, across languages and libraries, the details on how this kind of rank polymorphism works or broadcasting works differs a bit, but all of them have this. You can take a scalar with any kind of ranked array and do this operation. On top of this, you can spell it this way if you want. You might be thinking, why would you ever want to do that? In certain instances where you're building these chains of operations, it is actually nicer to call a dot, you know, mathematical operation that's spelled out. So, because if you use the binary one, like you just saw, or I guess I can go 2 ahead because it's the the same thing here. If you do this operation, you have to parenthesize in order to be able to chain this. And sometimes that's a little irritating. So, pick your poison when you're reaching for these. But this is a really nice feature that I miss incredibly when I go to languages that don't have this built in. So we come back here, all of these operations, the one index ones, these are basically unary operations that are applied to every element. The binary ones are your simple mathematical binary operations, pretty straightforward. If we come back to this slide, so the rank polymorphism is one thing. Another thing that I want to point out is you'll notice these stars next to some of these operations. These are the generic versions that everything else in that category is implemented in terms of. So, if you have a specialized version, reach for that specialized version. But I still provide the generic version in case you want to do something that doesn't have a specialized version. So one of my favorite categories is the 2-index maps at the top of the second column. This is map adjacent, which is equivalent to the map or the adjacent transform in C++23. It applies a binary operation to adjacent elements. And these are incredibly common. Even though it's an algorithm that we got in C++23, technically there was an equivalent of it in C++98 called adjacent difference, not a view version, but an algorithm version. And the adjacent difference is the equivalent of deltas. That's where your binary operation is subtraction. You're just taking the difference of adjacent elements. And differ is the specialization where your binary operation is not equal to. So these are incredibly common. They actually are explicit in an array language called Q, which I kind of borrowed the names from. And so anytime you see a star, look first from the algorithms below to see if there is a specialization that you can reach for. Otherwise, reach for the generic version. And the last thing I want to say about this is the categories of algorithms. So I've skated over this, but this is one of the most important features of this library, is that implicit fusion comes for free with this library. So I've heard in the past from folks at conferences that they would love a thrust where it implicitly does the fusing for you. So in order to get fusion and thrust, you have to reach for the fancy iterators or the custom algorithms that have that fusion baked into it. You get it for free in Parrot. Basically meaning that anytime you chain operations together or build some computation, if adjacent operations are fusible, that's done behind the scenes and you don't need to think about it. So anything in the fused or conditionally fused when possible category will always be fused. And it's in the materializing operations that you're going to actually end up launching a kernel. So a lot of times you can build this like long chain of operations, and then if there's only 2 materializing operations in it, where a naive implementation in some other library might end up with 3, 4, 5 kernel launches, you're going to get the minimum number of kernel launches with Parrot. And that is all I have to say about this API, which brings us to our second problem, which this is a fun problem. These screens, I mean, on YouTube, if you're watching this in the future, you'll have no problem making this out. But this is, note, this is not a named problem. This is just a generic problem too. And this is a real code that was taken from an open source library called Paddle, which I believe, if my memory serves correctly, is Parallel Distributed Deep Learning Framework, PADDLE, even though the LE comes from learning. So this code is quite verbose. And there's no way that maybe even in the front row you can make this out, let alone the background of this room. So we are going to simplify this and look at this step by step. So first thing we're going to do is get rid of all the arguments and all the initialization, because it's not super important to understanding this problem. So it makes it a little bit more readable, but still not that much. And so we're going to ignore the entirety of this code. And so the point here is, note that I've added underscores to the name of this function. That was not the initial name. It's so that I've obfuscated what this code is doing. So at the end of this exercise, hopefully someone in the crowd or in the YouTube audience in the future will be able to tell me before I tell you what it is, what this code is doing. So we're going to zoom in and play Name That Algorithm, brought to you by Sean Parent. This isn't a rotate, but it is a something. And so we're going to zoom in on this. And my question to you is, what is this code doing? Raise a hand or shout out as soon as you know. And I will sort of start talking while you are thinking and drop hints along the way. So inner product, if you aren't familiar, is the old name for transform reduce. So you've got 2 binary operations at the end. One is doing a transformation on 2 sequences, and the other one is doing a reduction on the resulting sequence from that transformed 2 sequences. Your 2 sequences are defined by begin and n-1, so that's your first to your second last element, and then your second sequence starts at the second element. And then you initialize your reduction with 0. The binary operation that's doing the reduction is plus, and then the binary operation that's doing the transformation on your two sequences is not equal to. So does anybody know, after those hints, what this code is doing? Or, for bonus points, what the name of this algorithm is. And hint, it doesn't exist in C++, but it does exist in Thrust. Yes, I didn't hear what Sean said, but that's because his voice was quieter than the gentleman in the middle, and it's counting the number of different elements, which is kind of, the hint here is that the variable name is unique. And so what this is doing is, it's kind of a perverse or twisted use of inner product. You're looking at two different sequences where the source of that sequence is the same sequence. One is to the first, to the second last element, and then the other one is the second element. So effectively, you're looking at adjacent elements, and you're checking when are they not equal to each other. And that's going to return you true and false, which is implicitly convertible to ones and zeros, and then you're adding those up. So you're adding up the number of time adjacent elements are not equal to each other, aka the number of time you have different elements, not to be confused with deduplicate. So it's only different elements as they change. If you have a 10 at the beginning and a 10 at the end and different things, those are going to count as two different values. And this is equivalent to the C++ standard algorithm called unique, and there's an extension of that in Thrust called unique count. So you might be thinking, well, why did this individual do this twisted thing with inner product? At some point, unique count did not exist in Thrust. It was not a 1.0 algorithm. And I believe because this pattern was so common, this is a common thing that you do before you call an algorithm called reduce by key. It's a segmented reduction, where basically you're given a sequence, a binary operation, that anytime it returns true, it's going to basically create a new sequence that your reduction is going to be performed over. And so one of the first things you do before calling reduce by key is you want to know how many elements am I going to end up with after performing this segmented reduction. And so what do you need to do? Well, figure out how many times do these values change. So you're going to call an inner product before you do this reduce by key, allocate a device vector for the results of it, and then call your reduce by key, which, if we come back to this code, or actually, so we're going to take a small little digression on the implementation of this algorithm. So we just saw one potential implementation, which is a call to inner product, and we're doing a +1 because that's just the way it works. We need to add 1 in order to get the total unique in the terms of C++ unique elements. Another implementation, which I like better, is the following. Because inner product, it's so opaque. Like, you look at that code, and even folks that are algorithm experts, you have to stare at it for a second. Okay, you're looking at adjacent. Which binary operation is the reduction? It's very, very confusing for what is such a simple thing at the end of the day, because you're making use of an algorithm that doesn't really match the semantics of what you're doing. This code, however, I like a lot more because it explicitly points out that you're zipping, first and first +1. For me, that's a lot more obvious that you're doing something on adjacent elements. And then you have to kind of, type this black magic incantation of the transform iterator, which is passing a binary operation that you have to pass to zip function in order to make it work with the zip iterator. But then once you have that, you've got your not equal to on adjacent elements, and then you pass this to reduce. And so is this better overall? Slightly. Is it great? Not really. But if you go and look at unique algorithm, it's an algorithm that is implemented in Thrust. If you go take a look at the actual implementation of unique count in, this is open sourced underneath the CCCL repository, you end up with this. So if we skip, all the template boilerplate, and we get down to the make zip iterator, we just saw that. They have a slightly different version of the, first +1. They have a make tuple with first and thrust next first. And then they're calling a specialization of reduce, COUNTIF, which is an algorithm that I always forget about. Because I have an array brain now after having dealt with array languages, and I'm so used to just doing reductions on Boolean sequences that I forget that COUNTIF is a specialization in C++ that is a reduction that takes a unary predicate. So you can skip a lot of the times like applying that unary predicate and then calling a separate algorithm. So when I saw this and I was like, actually COUNTIF is slightly nicer there. So if you go back to my code and use a COUNTIF, and you've got this now. And this is pretty nice. The problem here, once again, is the same problem that I pointed out when we were looking at the transform reduce sum of squares example. We've just seen 4 different ways to code the exact same thing. The first 2 weren't great. This one's maybe a little bit better. But the point being is, like, how are users or LLMs supposed to know which one of these to generate? And the goal is to not just simplify this, but give the LLMs a nicer target. So this is map adjacent. It's an actual generic algorithm that we have in C++23. It exists in Parrot now. You can pass it a binary operation, .sum +1, and you're done. Or for the astute listener or viewer, there was a specialization that we had for this. Differ. So these are the only two ways. I mean, technically, you could use reduce and then pass that a binary operation as well. But other than being able to reach for a more specific version of the algorithm, like this to me is very motivating for why you should reach for Parrot than alternative libraries. They work in the same ecosystem, so at times, Parrot's not going to be as flexible as other libraries that NVIDIA offers. But in cases like this, I think this is like a huge win in terms of not just readability, but you're having to type it out or getting a tool to generate it for you. So I believe that is the point that I want to end this digression on, is that we've got these kind of hand-rolled algorithms on the left from Thrust, transform, reduce, unique count. Tabulate is one that I haven't mentioned, but it's a counting iterator plus a transform. And how do we know when these specializations exist? If you're an expert in Thrust, you'll know, so you can just reach for it. Other times, you have to juggle the fancy iterators and the algorithms. In Parrot, the goal is I provide you a simple API, you chain stuff together. You don't ever have to reach for map reduce. It doesn't exist. There's just map, reduce, the fusion is behind the scenes, and it's the best of all the worlds. That is the end of this digression. So let's go back to the paddle example. I've now injected the unique count, and so this is almost readable at this point. If we reformat this a tiny bit, it's now, if the screen was a little bit better, we could argue that we can reason our way through this. So the first algorithm that we make a call to is sequence. That we saw before. That's our sequence generator, our IOTA sequence. And then we're making a call to sort by key. So we've got our data, we've got our indices, and what sort by key does, it's a bit of a confusing algorithm. It takes two separate sequences and sorts them both based on the first sequence, which is actually not what I thought this algorithm did when I was reading the code. Because sort by key, a lot of the times the key means you're applying a unary predicate. So if you have strings and you want to sort by their length, that's something that I thought sort by key could be used for. You want to sort by some key selector function, and then based on that, you're going to rearrange it. This is similar, but it's actually sorting two different sequences based on the first sequence. So if you were to put your two sequences in a container of pairs, and then to sort that container of pairs, that's effectively the same thing without having to bundling up everything up into pairs together. So now we've got our data sorted and the corresponding indices sorted as well. And then we're making our call to unique count, which is just setting up for the number of outputs from our reduce by key operation. And we're setting up the data, keys data, counts data. And then we're making a call to reduce by key. We're using the default binary operation that comes with reduce by key, which is not equal to. And then we are calling the data as our reduction sequence. So that's what we're reducing, or that's our sequence that we're choosing our segments on. But our reduction sequence is actually different. It's just a constant iterator of 1, which means that the reduction that we're performing is we're counting the number of times a contiguous equal element shows up. So we're basically getting the length of each contiguous segment, which, because we've sorted our data, we know that now we only have elements that are equal to each other next to each other. So this is a fancy way of getting what's known as a frequency count. How many times does each unique element show up in our data? So once we've done that, we're now calling a max element on the counts. And then the code at the bottom of the screen is doing kind of some arithmetic to back out the index of that element that was found by max element. Does anybody know the name of this operation? There's a couple different names for it. No, for the operation overall. So distance was the guess, but so if you bundle all of this up and had to name this function, argmax. Not the full. That's not the full name, but you could, yes, the last little bit from max element on definitely could be argmax. So this is an operation in statistics called mode, which is what the name of this function is. Or in other languages, they just call this most frequent. And so the question is, how would we solve this in Parrot? So this is kind of cheating, because I'm making a call to a mode function. So we've just evaporated everything. But I only added this after I had actually simplified it using the existing algorithms. And so if you're not going to cheat and use a built-in one-liner for this, this is how you would solve it. For each row in your matrix, you're going to call .row. You're going to sort it. RLE stands for run length encode, which is going to give you pairs of basically the values and the counts of each of your elements. Then we do a max by key, which is going to get the maximum based on a predicate here. And so because we have pairs, second is what we want to get the max on. And then once we've done that, we just want to pull out that value. So even if you're not using the the mode shortcut, this is still, in my opinion, much preferable. And the really nice thing, I don't have it shown here, but if you're building this up, you can just keep a dot print at the last thing in your operation. And so as you're going, the output of .RLE is going to be a nice kind of, if you're familiar with the format library or what's in C++ 23, it gives you a nice, human-readable tuple, container of tuples with, comma separation. It's very, very nice. And building this up kind of feels like if you've ever been inside of a Python REPL or a functional language REPL and you're just building things up one by one. It's very, very nice. And that brings us to our last example. I mean, I technically do have a bonus, but we'll see how long this takes, and we might just open it up for questions. So softmax is an operation from machine learning. The details of it don't really matter, but Bryce and I and a coworker were chatting a lot about it over the last 2 or 3 weeks. And in Parrot, it boils down to this. You initialize some kind of matrix, and then you are going to do a row-wise max reduction, so get the max element from each row. And then you are going to replicate that result because you want to subtract the maximum of each row from each element in that row. So that's basically the matrix.maxr with the template 2. That means do a row-wise maximum. And then the replicate means replicate by the number of columns, and that's going to give you a value for each element in your row to do the subtraction from. So then you do your matrix minus those values, and that's going to do that subtraction. Then you do exponentiation, and then you do something very similar. Now you still have a matrix, and you do row-wise summation, and then from that, you want to replicate again, and then your final binary operation is division. So we have, what is that, 4 or 5? We've got a max, which is a binary operation, subtraction, exponentiation is technically a unary operation, plus reduce is a binary operation, and then we've got division. So 4 binary operations, 1 unary operation. It's pretty straightforward, and what I want to highlight now is the profiling tool that's bundled with Parrot. So I call this KP, it's short for kernel profiling. If you're familiar with any of the NVIDIA profiling tools, there's primarily 2, NSYS and NCU, which stands for Nsight Systems and Nsight's Compute. I primarily use NSYS, but if you've used it, is a little bit tricky. It's got a lot of command line arguments. A lot of the times you're passing them the same thing. And so I've built a tool which is basically just a Python script that wraps this. And this is what the output of it looks like. So you type KP, you point it at a folder, and the folder can consist of CUDA executables or Python files. And it looks cool here, but we want to see if we can skip to the interactive version. And so this is the results of a softmax across the orange logos, TensorFlow, JAX is out of Google, Parrot is my library, CuPy is a CUDA accelerated version of NumPy, Thrust is the library that I've mentioned a few times throughout this talk, and then PyTorch is on the far left. And the really nice thing is you just point it at a folder. It's going to run NSYS in the background and then generate you all the data files, CSVs, JSONs that you need to. And then I extract out this and create a nice little visualization. And the really cool thing that I use this for all the time is that you can hover over each of these, and it it tries to do as good a job as it can as like truncating the very long names of all of the kernels. So if you go to the Thrust code, you can see that Thrust is built on top of another library called cub, and this is dispatching a bunch of transform kernels, the device segmented reduction. And this, I should say, is not fair to Thrust. I did not feel like going and writing the Thrust code for a softmax computation. Because it's very tricky. And so I just asked Claude for, given this parrot code, and you have all access to the source, go and give me a non-parrot version of this in Thrust. And it went from the 4 or 5 lines that was there. In a single shot, I didn't have to fix anything. It gave me, I believe it was 178 lines of Thrust code. That being said, it didn't do the optimal thing the entire time. You see a bunch of transform kernels because where it was using a transform algorithm, it should have been using a transform iterator. And if I wanted to, like a lot of the people, they say, oh, this is why LLMs aren't that great. They are great. It, in a single shot, wrote me 178 lines of CUDA code that compiled. Sure, it didn't do the optimal thing, but that's why engineers are still going to be employed for the next few years at least, or months at least, is because I have the expertise to know, okay, I know what this operation is doing optimally. We shouldn't have to launch any of these transformations. And so the next thing I ask is say, okay, all those transform kernels, you can reach for a transform iterator. Please do that. And a lot of the times, the value is that I don't have to type anymore. Like, I am still holding this model's hand to get to the right thing, but it just saves me so much time. To write 178 lines of CUDA code that compiles in the first shot, it's not even possible. So yes, anyways, the point being is I didn't go and optimize this. I just wanted to be able to throw it on the screen. But the point being is you can go underneath, and so PyTorch comes out of Meta, formerly Facebook, when this thing was released, and you can see that there's a bunch of they've modified the namespaces, but this is built on top of cub as well. And the very curious thing about this, the reason I wanted to show this is it's a very powerful tool. If you don't know how to use NSys, you don't need to know. You can just go make use of this script. It's in the scripts folder under KP. But you can see that this is the optimal code that we're looking for. But why am I showing this? Because 2 other frameworks, JAX and TensorFlow, are beating me. Well, that's because the only solutions that beat me are libraries that are able to optimize and see that the Python code is actually a softmax calculation, and then they've dispatched to a bespoke kernel for this. That is literally named softmax2. The 2 is for the row-wise, because you can also do softmax just on a single array. And I thought this was crazy that the code that I didn't write it, the LLMs wrote it, but I went and checked because there are actually softmax operations in a lot of these machine learning libraries or data science libraries. And I thought, oh, well, maybe what it did is it saw that I was doing softmax, and so it just went and called this custom function, which is kind of cheating, right? But it was not. It was actually a function that was doing all the same binary operations, and it was, I guess, the JITting technology. You can notice that a lot of these have 2 different versions. So one of them is a naive version that's not JIT compiled, and the other ones are using decorators in Python to call a JIT compiler. So in the JITting process, they are able to recognize this is a custom computation that's very important. Let's dispatch to a bespoke kernel. So unless if you have a library that is doing this bespoke dispatch, Parrot is going to be very, very fast. So a very cool tool. And I believe at this point we're going to switch back, which leaves us with, I believe, still 20 minutes. So I'm going to skip past a bunch of slides, and we'll come back to these. And I do have, so this is the first time I'm giving this iteration of this talk, and I changed a bunch of stuff, and I thought, well, I don't actually know how long this is going to take. So in case I had the time, I have a bonus example that is a example that I've talked about in 2 or 3 different C++ talks at the conference that I think Sean and I were last at together, was C++ on C. Actually, we might have been at one in between then. But that was, I believe, in 2023. I talked about this problem. I also talked about it in a CPP North conference. But this is a problem that I love. It's a trivial, coding challenge problem, but it highlights a lot of operations that are very, very common when solving algorithmic things. And I'm not going to go over it, in the 30 minutes that I cover it in those other talks. Go watch one of those talks online if you haven't seen them. But the basic principle is you're given a sequence of integers. which are supposed to represent fish. So there's only two numbers. It's 1 and 2. 1 represents the blue fish, 2 represents the brown fish. And the problem states if you and your friend go to the restaurant and it sets a bunch of rules, you're only allowed to grab a sequence of blue fish in a row and then a sequence of brown fish in a row, and you have to get the same number so that your friend or you aren't upset that he got more sushi or she got more sushi than you. So the question is given this sequence of elements, ooh, a little Microsoft bug there, what is the maximum number of sushi that both of you can eat together? So you need to look at adjacent sets of sushi, figure out where the longest sequence where you can get the equal amount is. So as you just got a little preview, the answer here is 4, because you can get 2 blue sushi and 2 brown sushi. The answer is not 5, because if we add the third blue sushi, you no longer are meeting the criteria. It has to be equal numbers of blue and brown. And there's an alternative. This is giving you the answer before as well. But here the answer is 6, because we've got 3 in a row, and then for both the blue and the brown, and so we add those up and we get 6. So this was, in that talk, the non-ranges version. And I said then, and I will say again now, the point is not to look at this code and to read it and to understand it. The point is to look at it and go, that's a lot. That's a lot. We've got 4 local variables. It's a very, very imperative solution. We're constantly mutating this stuff based on a bunch of different things. And the point is I don't ever want to have to write code like this. And then I go and I show a bunch of solutions across different languages. I showed a Circle version, which I think Sean also mentioned, or you mentioned the safety proposal. That was built into Circle. Circle has kind of been put on hiatus because Sean Baxter now works for NVIDIA and is working on other things. But this was the best version that you could do in C++ without these Circle add-ons. So you're making calls to a bunch of ranges, views, functions. So I believe this is actually using the range v3 library, because at the time I gave the talk, the standard hadn't implemented all of the C++ 20 and 23 views that I needed. But you can see that this is kind of messy because we don't have the ability to pipe all the operations. Some of the operations, if they have variadic overloads, are not pipeable. Therefore, we have to store things in local variables. And it's just still not great. It's better than this code, but it's still not fantastic. And the point being is now you can solve this problem in Parrot the following way. And this is kind of when I am trying to look at the solutions to code, this is the style that I expect Parrot to be used in. It's this chain, it's kind of waterfall of operations where, the first thing we're doing is we're looking where, elements are not equal to each other. Where is a function that gets you the indices of where those inequalities are happening. And then we do a prepend and an append of 0 and the length of our sushi list. We can then call deltas on those indices to get the length of each of the sushi segments. And then from there, all we need to do is look at the minimum of adjacent lengths and then find the maximum of the minimum of those adjacent lengths. And then we multiply it by 2, aka double, which I had to drop the O and the U for because that's a keyword in C++. So if you are upset by the name of double, open an issue, open a PR. I am happy to, this is a research library that for the last, since April, I've been working on. And therefore, I, am the dictator that gets to choose everything. But now that it's out in the wild, if folks have, things they'd like to see or changes they'd like to see, contributions are welcome. Anyways, this is the type of code that I hope to see in the world. And implicit here is implicit fusion. So there are only 2 kernels launched here. One is the reduction at the very end and the maximum, and the other one is in where, because where is a compaction. It's taking a list of indices and a list of Boolean values, 0s and 1s, and materializing the indices that correspond to the 1s. So that's going to be a thrust copy if behind the scenes. Everything else, differ, prepend, append, deltas, map adjacent, double, which is just a transform, these are all fusible operations. And to write the equivalent without having this implicit fusion is very, very thorny. So that's the last example. So now at this point, I can go back to the final slides. So yes, Parrot, it is open sourced as of an hour ago. Feel free to go check it out. Like I said, issues, stars, pull requests are all welcome. And with that, I will say thank you. All right, so I've added one, initially I added one corporate slide. So this is a free instructor-led CUDA C++ training. And then Bryce also asked me to add this one. We also have free GPU credits for a CUDA C++ tutorial. So if you want, I mean, I think you can, if you miss the QR code here, for whatever reason your thing is not working, you can find it down at our booth. We have a TV that has these QR codes just on a loop. So yeah, feel free to check out the booth. And with that, I've been told we have 10 minutes. I can throw this around, and I'm happy to answer questions.
Test. Okay. So how does the library work internally? Like, how does it do the fusion? Does it generate kernels at compile time, at runtime? How does that implement?
So yeah, the question, well, I assume the mic picked it up, was how does this work internally? This library is built on top of Thrust. So it basically makes what you had to do manually before just happen automatically behind the scenes. So there's no jitting or anything like that. All the kernels, I mean, there's a couple places where it relies directly on cub. But basically, internally, it's just building a nesting of these iterators. So when you make a call to a one-index map or a two-index map, that is a call to a transform iterator from Thrust, or a zip iterator plus a transform iterator from Thrust. And so it's not dissimilar if you're familiar with how ranges work in C++. It builds up this chain of kind of, what are they called? RACOs, range adapter closure objects, which if you've ever built up like a chain of these, you're going to end up with a template error that's kind of thorny. So it's not dissimilar from how ranges works.
Okay, thanks.
Thanks for the question. Other questions?
That's a bit far, but I'll try.
Oh.
I have a question. When you're reusing a piece of functionality, you're basically wanting to plug it into two different computations. Can you do sort of like a point-free solution, or do you have to basically define the first part of the result, store it in a variable, and then reuse that variable in two places?
Yes, so the question is, can you do a point-free like thing instead of materializing things in like a named variable? Currently, I have no support for combinators, if you will. Like fork and t is what they're called in functional languages, but they're called other things in other languages. Earlier iterations of this research had combinator support, but through discussions with colleagues, I was convinced that they were not the most readable version of the code. And so, although I do have a soft spot in my heart for those kinds of point-free solutions, yeah, they currently don't exist. That being said, like I said, pull requests, issues are welcome. If that is a style that many folks are interested in, it's something we could explore, yeah. But currently it doesn't exist in the library. Other questions?
Are there ways to customize this and extend with more algorithms? How do you compose them? And like, can you like make your own algorithm and put that on the after the dot?
Can you make your own algorithm and put them after the dot? Not in the way that you've seen. So, I mean, with the generic operations, if it fits into one of those, you would just basically call the dot map or dot map to for one or two index operations, and then pass your device annotated lambda, which has that bespoke operation. A lot of the times, honestly, like I've seen people do that kind of thing, but you can actually just, the equivalent is just making a call to the binary operations or unary operations that are in that lambda one at a time, and then it's the same thing. If you're asking, what if you have some crazy statistical thing that you can't express with a map or whatever, that you currently can't do, but like I said, this is open source, so if it's a common enough thing, we're happy to take pull requests and add those kinds of operations. Thanks. I see no hands. If that is the case, yeah, I'll say thanks again, and feel free to find me after the talk is dismissed.